Okay, so let's solve today's daily integral problems. As far as I can tell, most of today's stuff is actually relatively easy, including the limits, so this should be a quick one. So let's start with the beginner integral. The beginner integral goes from 0 to pi over 2. It's square root of cosine x minus cosine x over cosecant x, but cosecant is 1 over sine x. So this is actually just this times sine x dx, and then if we let u equals cosine x, you get the integral from, well, the u is negative sine x, so you get the integral from 0 to 1 of square root u minus u du, which evaluates to, well, this is u to the 1 over 2, so this is 2 over 3 u to the 3 over 2 minus u squared over 2 from 0 to 1. At 0 it evaluates to 0, at 1 it's 2/3 minus a second, which is it would be 6. So it's 4 minus 3, so 1/6. And let's check this out on the the beginner integral. The answer is 1/6. Yes. Okay, moving on to the easy. The easy one is a simple trig substitution because we have square root of 1 minus x squared, and x goes from 0 to 1. So we will just let x equals sine of theta, for example, then dx is equal to cosine of theta d theta, and then if x goes from 0 to 1, theta will go from 0 to pi over 2. It's square root of 1 minus square root of 1 minus sine squared x, sine squared of theta, times cosine squared of theta d theta. Now this is the integral from 0 to pi over 2 of the square root of 1 minus, and this is the square root of cosine squared, which is just cosine squared theta, since cosine is positive on 0 pi over 2, times cosine theta d theta. Now, to continue from here, we will need to multiply the numerator and the denominator by the square root of 1 minus, well, we basically want to make the numerator have the sine term in it so we can do a change of variable. So we multiply both numerator and denominator by square root of 1 plus cosine theta. It gives us this. Now this is just sine of theta, which means we can do a change of variable and let t equal sine of theta. Then we get the integral from 0 to 1. And we get the, well, sine, no, we let t equal cosine theta, my bad. Then dt is negative sine theta d theta. But if we still apply the same boundaries of integration occur, so this is our dt, and this is finally the integral of t over square root of 1 plus t dt, which if we add and subtract 1 to the numerator, we get this, which we can easily see is just square root of t plus 1 minus 1 over square root of t plus 1, which evaluates to, again, 2 over 3 t to the t plus 1 to the 3 over 2 minus 2 square root of t plus 1 evaluated at 0 and 1, which is 2 over 3, 2 to the 3 over 2 minus 2 square root 2. And on 0, this evaluates to negative 2 over 3 plus 2. So I guess this is what this ends up evaluating as. Let's try to input this as the final result, and hopefully it works. So this is 2 over 3, 2 to the 3 over 2, minus 2 square root 2, square root 2, minus 2 over 3 plus 2. Yes, this is correct. And let's move on to the medium. And the medium one is actually an interesting, kind of interesting one. As usual, it utilizes some interesting tricks. I had a bit of trouble when I first saw it, but then I realized the following. So again, if I plot this function that I'm asked to find the integral of, notice that there is a symmetry point around negative 1/2, negative 1.5, which means that if we apply a transposition, like if we let x equal, if we let u equal to x plus 3 over 2, this will move our integral to the right by 3 over 2 units, which means hopefully there's going to be some sort of symmetry here. So now the bounds of integration go from negative 3 over 2 to 3 plus 3 over 2, which is 9 over 2. Yet the square root of x is u minus 3 over 2. X plus 1 is u minus 1 over 2. X plus 2 is u plus 1 over 2. And x plus 3 is u plus 3 over 2 plus 1 dx. Now, the funny thing here is that these are differences of squares, so we can merge them and get u minus 9 over u squared minus 9 over 4 times u squared minus 1 over 4 plus 1 dx. And notice now that this function is even, so we can actually drop the symmetric part of this interval and actually get the integral from 3 over 2 to 9 over 2 of square root. And now I'm going to do the expand the brackets in here. We're going to get u to the 4th minus 1 to the 4th u squared minus 9 over 4 u squared plus 9 over 16 plus 1 dx. This is the integral from 3 over 2 to 9 over 2 square root of u to the 4th minus 2 times 5 over 4 u squared plus 25 over 16 dx. What I did here is make a common denominator and write this in the form of a square. So when I continue, I'm going to get the square root of u to the 4th, u squared minus 5 over 4, all of that squared dx. And now this term is positive on the interval 3 over 2 to 9 over 2, because u is greater than 3 over 2, meaning that u squared is greater than 9 over 4, so u squared minus 5 over 4 is greater than 1, which is greater than 0. So the square root can be removed, and we don't have to keep an absolute value. This is just the integral from 3 over 2 to 9 over 2 of u squared minus 5 over 4 dx. Of, not dx, du. All this should be du. Meaning that this ends up as u to the third over 3 minus 5 over 4 u evaluated from 3 over 2 to 9 over 2. And so we end up with 27 over 24 minus 5 times 9 is 45 over 8 minus no, I made a mistake here. This is not 27. This is 9 times 9 is 81 times 9. 81 times 9 is 9 over 24 minus 45 over 8. Yes. Minus now 27 over 6. Not 6. 27 over 24 again. Minus 5, no, 15 over 8. So this finally evaluates to 7 to 9, so 702 over 24 minus 30 over 8, which, if we make a common denominator, is 702 minus 90 over 24, which is 612 over 24. And let's try to remove some common factors. 306 over 12, which is 153 over 6. This can be divided by 6. It's 51 over 2. So, and then there's a term of, 5 square root 5 over 3. So the result should be this minus 5 square root 5 over 3. So 51 over 2 minus 5 square root 5 over 3. That is incorrect. Interesting. Where could I have gone wrong here? Okay, I'll take a look and be back with you when I find where I made a mistake. Okay. So after looking at my calculations, I realized I'd made an error in that I said here that the function is even, therefore we can remove the symmetric part of the domain, but that's not true. The symmetric part of the domain has to remain because it's even. It just can be like 2 times the symmetric part of the domain. But that doesn't make sense because we have another problem here. If the symmetric part of the domain remains, then we have the problem that this absolute value cannot easily be removed. Specifically, if we see how the function's sign goes, it changes sign at plus or minus square root 5 over 2. So we have to split this integral into 3 integrals over subregions of the initial region. Specifically, subregions from negative 3 over 2 to negative square root 5 over 2, then a region from negative square root 5 over 2 to square root 5 over 2, which is an even function and is symmetric, so we can just do 2 times the integral from 0 to square root 5 over 2 to calculate it, and an integral from square root 5 over 2 to 9 over 2. Now, I'll save you the hassle of going through all of the calculations that are needed, but in the end, we end up with the value 24 plus 5 square root 5 over 3, And if we subtract 5 square root 5 over 3, we should just have 24. Yes. This was an annoying integral to deal with, but it wasn't hard per se. The only hard part was realizing that the function was symmetric around 1 over 1, or about around negative 3 over 2. Finally, the hard integral, as usual, I've already taken a look at to make sure that it can be solved within a sensible time limit. The hard integral is actually very easy to solve if you know something called Glasser's master theorem, which states that the principal value of an integral over R of f of x minus 1 over x dx is the same as the principal value of an integral over R of f of x dx. We're asked to find an integral over R of a function that is 1 plus x squared plus 1 plus x over x squared times 1 times 1 plus x minus 1 over x squared dx. The idea is that if we can make the term x minus 1 over x appear on this left side, we can use Glasser's master theorem to completely remove this term and turn it into a normal x. So the way we're going to do that is we're going to apply a well-known idea, and that is that this value squared is x squared minus 2 plus 1 over x squared. So we will add and subtract 2 here and get x minus 1 over x squared minus 2 plus 2, we subtracted 2 to make the identity, so plus 2 plus 1 is plus 3. So this is just the integral over R of x minus 1 over x squared plus 3 times x minus 1 over x squared plus 1. Using Glasser's master theorem, this is just the integral over R of 1 over x squared plus 3 times x squared plus 1 dx. And would you look at that, this is just partial fraction decomposition that we can do here. The way we're going to do it is we're going to write this one as a 1 over 2 times 2, and 2 is 3 minus 1. So we can just say x squared plus 3 minus x squared plus 1 all over x squared plus 3 times x squared plus 1. And split this integral into two other parts. You get 1 over 2, 1 over x squared plus 1 dx minus 1 over 2, 1 over x squared plus 3 dx. These are just inverse tangents, so this is 1/2 inverse tangent x from negative infinity to positive infinity minus 1/2 times, well, this is a square root of 3 squared, so this is 1 over square root 3 inverse tangent of x over square root 3, also evaluated from negative infinity to infinity. So finally, at infinity, this evaluates to pi over 4. At negative infinity, it evaluates to negative pi over 2 times the negative because because it's the lower bound, so this will be a plus 5 over 4 again. And then we have minus 1/2 times, well, 1 over root 3 pi over 2 plus 1 over root 3 pi over 2. Finally, we get pi over 2 minus pi over 2 times 1 over root 3. We can take the pi over 2 out, get pi over 2 times 1 minus 1 over square root 3. And let's check our answer. And it's correct. This was a relatively easy hard integral, provided that you knew Glasser's master theorem. Otherwise, you just have to go and do partial fractions like twice on this and evaluate using principal value semantics to make sure that some things cancel out. But it can be computed without the theorem. But with the theorem, it's a very short calculation. Finally, let's do the limit. And the limit is, again, one of those limits that L'Hopital's rule can work on immediately, but I'd rather not use L'Hopital's rule because how are we learning analysis if we use L'Hopital's rule for everything? So what we're going to do is we're going to write this as the Taylor series expansions of e to the x, which is x to the k over k factorial, or we can write this as 1 plus x squared over 2 plus other terms of the order of x squared of x to the third. We can also write the cosine as its Taylor series expansion, x to the 2k over 2k factorial, which is it's for 0 it's 1 minus x squared over 2 plus terms of the order of x to the fourth. Now, what we want to do is calculate the limit as x goes to 0 of e to the x minus cosine x minus x squared over 2 all over x squared. If we substitute with these approximations, we get 1 plus x squared over 2 plus terms of the order of x squared minus 1 plus x squared over 2 plus terms of the order of x to the fourth minus x squared over 2. And notice that the ones cancel, the x's cancel, 1 of the x squared over 2 cancel, and then we get stuff that's of the order of x to the third. We get x squared over 2 plus stuff that's of the order of x to the third, all over x squared, and this will give us the limit as x goes to infinity of 1 over 2 plus something of the order of x. Of course, something of the not infinity, to 0. It goes to 0. Of course, something that's of the order of x as x goes to 0 also goes to 0, so this is just 1 over 2. And let's check our result. And it's correct. Okay. Thank you for watching, and this has been a fun day, but mostly grindy. Like, this medium integral took way too much time for it to be worth it, but the trick in the beginning was interesting. Thanks for watching. Today has been a grindy experience. Hopefully tomorrow isn't like this, but I'll keep my hopes up. Again, thanks for watching. Keep integrating, and see you next time. Bye.